This is problem 2-112. It's on page 105. Consider a classroom for 55 students and one instructor, each generating heat at a rate of 100 watts. That's the people. Lighting is provided by 18 fluorescent light bulbs, 40 watts each, and the ballasts consume an additional 10%. Determine the rate of internal heat generation in this classroom when it is fully occupied. Now, why would you care? Well, you would care because if you want to maintain the temperature constant, then you'll have to pump that heat out. So 55 students and one instructor, 100 watts per person, 18 lights, 40 watts per light, and 4 watts per ballast. So that's 10% of the 40 watts. That's where that came from. And of course, I'm going to assume that there's 1 ballast per light. Well, what's the heating load? Well, each person gives off 100 watts and so on, so all we have to do, count it all up. 56 people, 100 watts per person, plus 18 lights, 40 watts per light. Let's do it this way. Plus 4 watts per ballast. And of course there's 1 ballast per light. So lights and ballasts are essentially the same unit. It gives us a total of 6,392 watts. And it's kind of interesting to look at this and compare. A lot of people have an idea, they think they're going to get rich because let's make an exercise club, and in this exercise club, instead of paying the electric bill, we'll hook up all the treadmills and all the bicycles and whatever we've got to generators instead of just weights or just friction. And what we'll do is we'll use all of that energy to drive the lights. Now when you start looking at a human being's power output, in fact, let's go through and do that because this is an easy problem. There's the answer. But let's analyze this for interest. How much power can a person put out continuously? Well, if you're going to the gym, you're probably not an athlete. That's why you're going. Now, of course, athletes go to gyms too, but a lot of people try to get into shape. They go to gyms. That's probably the bulk of the clientele. So, in any case, an athlete can't put out a whole lot of power continuously. Maybe a horsepower or so for short duration, but not extended. In fact, a good athlete will put out about a quarter horsepower continuously for, a decent amount of time. So let's just be generous and let's just say we've got all decent athletes in our health club and each puts out a quarter horsepower. How much power are we talking about there? Well, if we've got, let's change this now to the gym. We've got 56 people in the gym, each one putting out a quarter horsepower. Well, 56 divided by 4 gives us 14 total horsepower. Because remember, each person outputs 1/4 horse, so it takes 4 people to equal 1 horsepower. So 14 horsepower. How much power is that? Well, go to the back of your book and let's do a conversion. 1 horsepower is 0.7457 kilowatts. Okay, so we have to multiply that 14 horsepower by 0.7457 kilowatts. I'm sure I got that right. I feel like I'm missing a number. Yeah, 7457. That's about 10 kilowatts. Now notice that the heat output of the people doing nothing was 6.4 or so kilowatts. Now, I've just computed that the work output of the people would be about 10.4 kilowatts. They were in the gym instead of just sitting in the classroom. Okay, so I believe that this classroom number is reasonable. But if you're just working out in the gym and all that's happening is your working against friction, then all this work ends up just going into heat, right? Think of a stationary bicycle with a belt around it. I know that's an old example, but most systems work that way. Most exercise equipment, all of the energy you expend goes into heat. And so thinking about this, we look at this number and we say, well, 10.4 looks like our idea works because look, we can probably draw these 18 lights. That might be enough to keep the club well lit. Great, things are looking good, but here's the problem. Do you think there's any inefficiency here? Well, yeah, there's going to be some inefficiency. The people are going to get hot, they're going to sweat. They're going to want air conditioning. You think the excess here, that extra 4 kilowatts is enough to drive an air conditioner for that many people? I don't think so. So this is nowhere near the energy requirement of a commercial building, so this simply wouldn't work. So anyway, it's an interesting idea. People think of ways to save the energy and store it, but you probably want to store it as electrical energy, right? Electricity, that's the easiest form to use. Well, electrical energy is just not easy to save. Now, the only practical version of this I could ever think of was, what if we were to make all the machines work together to raise weight? Maybe it pumps water, I don't know, it doesn't matter. Elevate, so storing energy and potential energy. You could try that. You'd need a fairly large mechanical system to do the storing, and if you're paying for the commercial property on a per square foot basis, it's probably cheaper to buy the power from the electric company, so this is not going to fly. So anyway, to answer the question that the author poses, about 6.4 kilowatts. Oh, by the way, and don't forget, this 10.4 was with all athletes, and probably some of our patrons will not be so athletic.